All right. Hi, everybody. I'm Ryan. I want to acknowledge there's a whole bunch of students who've worked on this work, and we're continuing to do it. So there's some in-progress stuff here as well. I'm going to basically divide the talk into two different sections, but they do relate to each other, and we'll tie them together at the end in terms of what we can do with SmartNICs on large systems and what we can do with some new composable infrastructure that's in this space. I want to acknowledge some of our collaborators, with Sean Bine and Scott Levy from San Diego National Labs as well, that have been involved in this work. So let's talk a little bit about how we got where we were with SmartNICs in the first place, right? SmartNICs were not a product developed in the presence of a problem. They were a problem on the product development side that ended up in a solution that now we have to figure out how to use, right? So the problem was when we started growing NICs and NIC architectures, we started doing some things with regards to the pad space that we needed, which led to the definition of how you build the actual dies for these NICs. And in that, you ended up with a whole bunch of blank silicon that you actually weren't using in the NIC logic. And so everybody was like, hey, can we fill these places in? And the answer is yes. But then people said, okay, now that we've added these capabilities of SmartNICs, what do we do with them, right? And at the same time, we've also got, accelerators really driving your server architecture needs. How many GPUs can you cram into a system at once? We've got lots of different stuff happening all at the same time in this space, right? There's also been some interest in disaggregated systems recently. What is a disaggregated system, and when I mean it in this way? What I mean is these are the people that are not buying NVL72 racks from NVIDIA and paying 3 million bucks for them, right? What they're doing is they're buying these things that are called chassis that have a whole bunch of PCIe slots in them. And you can pretty much plug and play whatever you want into those slots. And these boxes then attach with special fabric cards over to your servers. And you can wire up whatever's sitting in all of these different chassis boxes that look like local PCIe devices in your native servers. So you can mix and match, make server have weird things in it. You can make it have 32 GPUs in it if you wanted to, because you can actually feed that. That's really an AI use case, and you better have the bandwidth to go along with it. But you can do things like mix and match different components. You could go over to more specialized accelerators. It's a way to mix and match stuff. It's great for flexibility in like an academic environment when you want to test bed to in this space. But it's not just memory like we've seen in the past, like liquid and gig IO type systems. And so we've been thinking about these things and also the intersection with SmartNICs. What does it mean to have a SmartNIC that has its own operating system, something like a Bluefield, that's also sitting in a chassis, right? So now I have a CPU and I have memory infrastructure and it's connected to PCIe, but then it's also connected to servers. And there's lots of stuff going on in the middle, right? And we can also think about SmartNICs in terms of how they add to our traditional server architectures as well, right? Because we're essentially layering a host on top of a host in many of the different ways. So this is how all of those things start connecting together. So we've got SmartNICs, and if we've got SmartNICs in our system, and if you talk to some of the vendors in this space, they tell you that you might just get this because that's what we're going to ship you, rather than like, hey, you just wanted to buy the network. I don't care. You're also getting these cores. And so if you start getting this stuff in your system, what can we also do with these things that don't require application effort on individual applications? So there will always be some things that you can do with individual applications. If you're interested in what you can do with individual applications, we had a collaboration with Georgia Tech back in the day that looked at individual applications and what you can do in that space. But I'm really interested as a system software person in how can I use these SmartNICs to give me all of the wonderful things that I would like to be able to do in a system to help manage resources, drive traffic, understand what's going on, log things, exchange data and information that otherwise would have been impractical to do because I'm using networks and I'm using the components that I actually wanted to do compute on to exchange all of this information. So all those talks over all of the last 20 years where somebody says, hey, I tried to optimize this thing or do this better thing with resource allocation. And the trade-off was you have to give me some of your compute to be able to do that. And then people say, I don't want to be able to do that because I want to make the compute do the compute. I don't want to manage my resources because it takes away from my compute resources. SmartNICs give us an opportunity to do something that wasn't really a high value compute resource, but that we can run other system services on. And the benefit to this is we've basically taken SmartNICs and now we've found a system-wide usage for them that can help us improve performance. It may not be as much as if we purpose built and designed them for a particular application, but we can spread it across all of our applications with no application effort on part of the programmers, right? So we can also do interesting things in this space with PCIe address translation, where we can also bridge our networks to compose server nodes and architectures where we want. So looking forward, and I'm not going to represent that we can do this today, but looking forward, imagine the idea that you could malleably create uh, nodes, quote unquote, in very big quotes. Node is a very malleable term, right? Where you can create small SmartNICs feeding architectures control, where the real data is actually flowing from the storage system. So in this way, you can start thinking about how we can start creating new architectures. I don't want to represent that those are the highest performance architectures, but they may be very good architectures in terms of performance per dollar, right? In this space. So let's first talk about SmartNICs and the stuff that we can do with SmartNICs, and then we'll talk about how all of this fits together in terms of composability as well. So like I said, DPUs are still relatively new. They've been out for a while, but we're still kind of finding that killer app in this space, right? Because of the hardware design predating the software. And we don't really use them for applications quite yet. So if we take that stuff that I was talking about, system software, we can start doing new things where we create management layers, we can help with dynamic resource allocation. We do all this stuff that we want to do in terms of resource management and even managing reliability solutions asynchronously. So these are things that build in capabilities to be able to manage our checkpoints and other things like this that are independent of our compute software themselves, right? Think about them as SmartNICs can be a helper that you can pass jobs off to. Say, hey, I need to go do this task. Like, get this checkpoint out to the storage system, and I'm going to go over and do the valuable computational work that I need to do, and I'm not going to stop. You just go do that task for me. So think about them as kind of personal assistant version of supercomputing, right? And this lets us build some shared resource schedules to avoid conflicts. So what could I be doing with SmartNICs to help avoid the I/O contention issues that we just heard about in that last talk? I can actually start building schedules and knowing ahead of time that my I/O is going to conflict between those two different jobs and start planning that out, right? So even though one job might go slower, offsetting them such that I'm not using the I/O system at the same time, I can try to reduce variability in those solutions as well, right? But then this is stuff that we've been working on first. We first wanted to solve the problem of, in case the applications, SmartNIC's getting in the way, right? So if I'm busy exchanging a whole bunch of data about trying to not conflict with everything, and then I am myself am conflicting with everything from the SmartNIC software, I've completely defeated the purpose of bothering to do it in the first place, right? And we know that system software priority in this space is lower than the application priority because we don't want to slow down the application, right? And the network's a shared resource, so we have to manage how we do this. And so we've taken a long walk in trying to learn how to get out of the way in good ways. So getting out of the way for the SmartNIC just to get out of the way of the network is a lot easier said than done. We thought this was going to be a very short project, and it ended up being a much longer project than we wanted. But it was very important before we build these system software solutions to make sure that we didn't cause any harm. First, do no harm, and then from there, we'll manage our shared resources, right? I don't want to go into too much details with regards to how you predict traffic, but this meant using SmartNICs to try to help predict when the applications would be communicating and just avoiding communicating during those times. So we want to use the spare portions of the network. I'll say the quiet part out loud. Hopefully there are, okay, none of my funders are in the room. We don't use networks that much, right? We buy networks for their capacity, but most of the time we sit and let them sit idle. So we can find idle times in this space. It's not particularly challenging, but the opportunity cost for getting it wrong hurts. And when you look at something like this is just the port received data for how a molecular dynamics code works. This is LAMPS. We can see that there are periods when we're not, this is incremental traffic as it happens. So this is just, the total number of MeB bits that we have over our sampling frequency. I won't get into the sampling frequency over time, but you can just see that there's relatively some areas where the application is doing compute. It's not particularly communicating, right? And if you just throw this at a blue field and you say, okay, fine, I'll just go and I'll just run some ML libraries for it. What can I do in that space? You get a horrible inference time. It's awful. Okay. You probably shouldn't be using Bluefield straight out of the box to do any type of AI. It's not particularly good at it. But that led us down the road of, hey, I can do 58 prediction slots per second of using my network. Those are pretty damn big network slots, especially at the bandwidths that we have. And so we didn't want to do that. And so we saw that it's too expensive and we didn't get the accuracy and recall methods that we wanted. And so we really went about trying to build a better accuracy and recall tool. We ended up with a weird hybrid architecture in this space to be able to provide the performance that we need, but get the accuracy that we want. So what we did was we first took some linear regression. Linear regression is like, I hesitate to even call it an ML method. It's really simple calculation, right? Hey, what's the slope of the line that's happening? And it isn't bad for a lot of HPC apps because they're relatively regular, right? The problem is that by definition, it misses the steep part of the curve. When new stuff happens, it by definition just will never be able to predict it. And so it doesn't give you a good enough result, right? We tried a whole bunch of other different ML methods and eventually ended up on a two-stage system, which I'll talk to about lightweight precision prediction a little bit more. I might be getting ahead of my slides, but let's talk about it now. We can drive that time down to 2/10 of a millisecond instead of 17. So we can do significantly better than that. This gives us a much better granularity in terms of our slots. And how do we end up doing this? We're doing this through a variety of different techniques. We can do even better when we use smaller trees and overall leaves. But what we're actually doing is we're taking the linear regression that's pretty good at tracking the trends over time, and we're training an ML model simply to tell us whether our linear regression is lying to us or not. And it captures the stages of the linear regression that can't be predicted by the curve. So when the curve bends and changes, the ML models can actually predict when the curve bends and changes. And so all we want to do in this space, remember, my goal is not to actually match the exact curve of when it's being used, right? My goal is to simply accurately predict when it is. And if I accidentally get a false positive, the network's being used and it isn't, that's not a penalty for me, right? It's that I don't want a false negative and accidentally interfere. And so we were able to drive this down to the point that we can do 107 times faster with inference than we could with traditional ML models. And we can layer that on to get all of the accuracy and capability to avoid interfering that we need as well, and still run a much, much lighter model. So we're doing a two-stage ML type solution in this space. Does it translate to other architectures if you bought a SmartNIC with GPU on it? Yes. I'm not showing you those numbers here because GPUs are really good at inference and you just get crazy high frequencies that you can do it. And it's like, okay, great. I'm so glad that I can figure out whether the next byte will be consumed or not, but it's not useful to me, right? So that there's a granularity in this space that is right sized for us. And we find that that's really viable on just traditional mainline Bluefields with just ARM cores. So we can do a lot there. And it still leaves us a lot of compute left on the Bluefields to manage predictors, system software, doing resource management. We're only consuming single percentage digits of the Bluefields, even at very high accuracy rates with these developed models. So all of this stuff that we've built here, where now can do no harm. Now we're into the area where we're managing resources. We're starting to build up things so that we can make resource sharing viable. Okay. This leads us into disaggregated systems. So disaggregated systems, you may have tried these for memory disaggregation. That's the thing I like least in disaggregated systems in this space. So let's talk about what modern composable disaggregated infrastructure looks like. And I'm going to concentrate on a few sub products here, but just bear with me and I'm going to generalize it for the sake of this talk, just so that it makes it a little bit easier to look at. Okay, so you've got a system with traditional CPU and memory servers, but you've taken all your accelerators out of them. So these servers could be just half decent CPU type things that are sitting over here that could be like 1U, little tiny blades, anywhere to just a traditional server that you didn't fill up with a whole bunch of GPUs, right? And you move these all over into these chassis, which for physical purposes are just big boxes you plug a whole bunch of PCIe cards in. But for the purposes of these disaggregation networks, all we're really doing is encapsulating PCIe over networks, tying things together with intelligent, transparent memory translation in terms of the PCIe domains, such that you can tie all this stuff together and just looks like it's all connected. Now you're going to say, that sounds awful for latency because I've just taken something that used to be very, very close to my CPU and I've moved it very, very far away from my CPU. And we will be covering that in just a short amount of time. But first, why would you even want to do this, right? There's some advantages to composability. Again, that we're not talking about the top 10 of the top 500, right? But the bottom 250 of the 500 might see significant bump from a lot of these technologies. And there's some benefits to being able to deploy them as well, even in that top space where you're looking at advanced architecture test beds, where you're looking at a lot of different things. You want to mix and match them together and have a lot of flexibility in that space. If it's so useful, why hasn't it been done before? Creating these decoupled PCIe domains and managing all the translations of the addresses such that you can actually wire things into a server, expose enough devices such that you can expose a large amount of equipment, like an entire row of supercomputing equipment, and not flood your PCIe bus and run out of IDs or make your BIOS have to hack. You have to hack your BIOS. Like adding more than 64 PCIe devices to a typical server, you probably voided your warranty by hacking in a different version of BIOS so it'll scan it. Because most servers, why would you ever have more than 64 devices? You don't have 64 PCIe slots, right? So why would you design something that would scan that many devices? Something must be wrong. We can get away with not actually scanning those devices, hiding them in an abstraction layer with some software in between, and still expose them only when we want to. So you don't have to hack the BIOS anymore. You can wire up to 64 things without changing anything, and you can pull them from pretty much anywhere all over the system. Of course, you need to be intelligent about where you pull those from, right? I already kind of talked about this before, but it's one of the elements of CDI, and accelerators are important because specialization becomes more viable when technology trends slow down. So let's look at the charts that illustrate this instead of looking at words. So over time, right, our performance in terms of per dollar and micro performance processor improvements, I'm just showing you CPUs. We all know they slow down, right? You're not getting your performance for free anymore. You can't just go to Intel and be like, cool, give me the next product that's twice as fast as the last thing. That is the exact same price as the previous year, right? And in that old day, right, CPU progress was so fast that if you went out and you developed a new thing, build a new chip to do specific thing. Let's just take, I'm going to develop it for molecular dynamics, just because we used molecular dynamics earlier, right? And I go out and I build a specialized chip. That thing in the old days, with the old curves, you had about 3 to 5 years max where you were faster than the general solution. And then the general solution caught up to you. So you have to amortize and be that much faster over that time period. And that's what we're saying in here is how fast you speed up from your specialization becomes more viable when you're in these blue areas. So you should specialize things even at low volumes. When you can get 100x speed up, you should do that, right? And this blue portion in here is when CPU progress is slow. So hey, our compute goes slower. It becomes more and more valuable to specialize. So I have to get something out of it. The amount of time that I keep ahead of general solution motivates me to specialize. But once you start specializing things, now you have the problem of if I buy a big gigantic supercomputer and I buy a ton of MD accelerators and stick a whole bunch of molecular dynamics accelerators in it, great. I just bought a really expensive molecular dynamics machine. I hope I have the workloads to fill that entire machine, right? So instead, when you can mix and match your specialized accelerators for users on the fly and you're not capturing equipment inside of systems, you can start piecing together systems that are cost viable with a multitude of different specialized hardware in them. Now, there's some performance trade-offs here, but we're trying to minimize those as much, right? So this is just trying to create your system design overall as being more flexible. So think about an alternative. We don't think about this from an HPC community, but you use this all the time. So anybody here seen anything recently on Disney, like The Mandalorian or any of the Star Wars series? Nobody watches Disney Plus? Okay. So modern TV shows that have sort of higher end production values, they're actually doing while they're filming them is they're filming them in front of green screens. And then they're using things like Unreal Engine to actually render the backgrounds. So all the backgrounds that you see in those shows are fake. They're rendered, but they render them in somewhat in real time, and then they make the final version later on, right? When you're doing graphics in that space or computer graphics, you're spending a lot of time working on your local system, and then you go out and you need to push them out to a render farm, right? That's a lot easier when your local system can basically just all of a sudden wire up some really big GPUs that are sitting over in a data center, use them locally on your local version of Blender or Unreal Engine, and then drop them when they're done using them. It's a completely different method than I'm going to reserve Slurm and I'm going to push it as a new job. It's just local on your own computer and you're just adding and subtracting compute in that space as well. So there's lots of different ways that we can think about these that may be complementary to an HPC type solution as well. Um, and those accelerators can have obviously big advantage over the CPUs. NVIDIA's made an awful lot of money on this concept, right? But we can't have those systems that have things like 16 GPUs in them or 32 GPUs in them because they're just physically impossible to build. Just we don't have the U factors in a rack to be able to do that and fit it onto a single board. So this is where how we get to things like NVLink switches and back bus bars and things like that. But you don't necessarily need that. Composability isn't exactly new. There's a lot of different composability technologies, and I'm not going to go into all of them here because that's the point of this workshop. So I'm hoping everybody is fairly familiar with this. But you need to be able to balance the composability and the flexibility of your system with the performance that you get. And from our initial experiments, and I'll start showing you some examples, some numbers soon, single row scale seems pretty possible and useful. So you get a large variety of different accelerators and devices that you can mix in. And you don't want to put them too far away from each other because the speed of light is still a thing, right? The problem is that if rack scale composability was easy, everybody would already be doing it in some spaces because this is the market. And you have to kind of blend your high performance computing network design and capabilities with PCIe chassis expertise and hardware people. So just getting these mixtures of groups together can also be troubling and difficult to do. So I won't bore you with the complexities of PCIe root complexes and how they end up getting shared, but there's a whole bunch of other things that you can do from a chassis perspective to provide those sort of, think of them as the home. When something gets lost or something needs to get routed to a PCIe bus, then not everything's on the same switch. It has to go back up to the root complex, and the root complex basically tells it where it's supposed to go and sends it back down. If that's out to the server, now we're taking light time back and forth in a row. Every time we want to communicate things, it's not efficient. We can do those things inside the chassis, though, to actually reflect stuff back into the existing chassis, and it significantly improves the performance as a whole. So this is something we've been working on as well. So we want to target a whole bunch of major communication libraries with these things. We've been working about collective communications and some of the elements in that space. We've been rethinking how collective communications happen when GPUs are very local. So what does it mean to have 32 GPUs that are all sort of local inside of a machine when you do collective rather than them being spread out 8 in a network? So we're actually doing less high-speed network on long haul in that space. And we had this idea in architectures that CPU to GPU communication is expensive, and people think that's also relevant to latency, and it's not as relevant as you'd think. It's very relevant to bandwidth, but not maybe necessarily as much as latency. So let's talk about that for a second. So when you've got a GPU, what are you doing? You're from the CPU side. There's two things that you're doing. You're either sending data to it, and there's multiple different data sources where you can get GPU to it. But essentially, the one thing that CPU does that no other component in the system does is send GPUs the commands. You tell it to run a kernel, you tell it to create a synchronization event. The CPU's sending commands, right? But the way that GPUs work and the scheduling that they do and the way that they build up their pipelines, GPUs basically are engines that you don't want to stop. You want to keep feeding them. Once you start them, you keep feeding them. They're hungry for data and you don't ever want them to stop. They're fast that way. What it means is that we actually end up sending commands about new kernels and things that we're doing next in our streams early on, where they actually get sat in queues for a little while before they actually get run, right? And this area here is what we call slack, because this command could have arrived later and it would have had no impact whatsoever on when the kernel was launched and actually running, right? So we looked at it and said, but that slack could be a big problem. We're high performance computing. We want to make sure that that it's not an issue. And so we ran a whole bunch of tests in this space, and the initial results actually suggest that the difference is in the noise. So if it's less than 1%, generally on large systems, 3% of noise is just the modus operandi, right? There's a lot of different sources of noise. And so if we look at some of the systems that we took out of this set, let's take a look at like Cosmoflow. Cosmoflow is a cosmological AI workload, for instance. You can add 100 microseconds, 100 microseconds, right? So on a fast network, round trip time between two nodes relatively close to each other is about 1 microsecond. You can add 100 microseconds to it, and it doesn't even show up as a percentage digit of slowdown, 0.5%. In terms of lamps, what was happening here? We're getting more variability on lamps, but still it's in the noise, right? It's less than 1% to go this distance. How fast does light travel during this distance? It's actually closer to transiting our data center in 100 microseconds rather than just going up and down a row. But I don't recommend that you get too close to 100 microseconds, right? So this makes me much more comfortable in terms of the space between 10 and 100, and that's definitely in the rack scale, right? Once you get up to adding a millisecond of delay, this is like going out and running your stuff on an old class data center, like where Google does its search. 10,000, you start seeing really big drop off. But this is because here is the transition between these 2 points is when we start falling into that slack. We've actually issued the command late. The GPU is now slowing down. It's not doing anything, and now we have to pay scheduling costs, and we've lost our pipelining. And so now we're looking at how do we end up pulling all of these things together and make sure that we can actually compose these things and not see the penalties in them. Now, I want to stress this. I've mentioned that these chassis are PCIe all over the place, right? So when we're comparing the speeds, these are against PCIe GPUs, right? We're not using NVLink everywhere and that sort of thing. These are the cheaper SKUs. So you're buying a cheaper GPU to be able to do this. So performance-wise, I don't want to represent this as you should just go out and buy this composable system and replace the top one system. That's not going to happen. But if you're buying the parts out of those SKU bins, essentially it doesn't matter, right? If you do this or not. And so you might as well get that extra flexibility because it lets us make them much more programmable. 32 GPUs that all look like they're connected to one server is a lot easier to program than having to deal with 4 nodes with 8 GPUs in them independently. You might not, for some jobs, not even need to deal with the fact that you have communication. And as an MPI person, that makes me sad a little bit, but at the same time, I don't have to deal with small jobs. And so what we're thinking about here is also ways that we can further expand this and reduce overall slack by combining our DPUs, because I can take a DPU, I can take a SmartNIC and plug it into a chassis. And now I have a local control system that's actually sending local controls that's still local, right? And I can compose together multiple chassis now too. So I can actually start moving my control closer light-wise to where it ends up being needed. Okay. And this brings us to all new sorts of new architecture types that you could think of in this space. And that's really being led by being able to have DPUs in a chassis. Yes, we have done this. We have brought up chassis that have DPUs in them. There's some interesting ramifications to that because DPUs kind of assume that there's also a host associated with them. So what we do is we compose in a host to basically poke the DPU and wake it up. And then we never really need to communicate from the host to the DPU ever again. There's also some still existing challenges with transferring root complex control over to that DPU. So we occasionally get spillage back to the original server, but it means that that one server can watch an awful lot of hardware because it's not doing an awful lot for the individual groups. And that lets us mix and match with other accelerators and bring in new specialized systems. So I keep saying accelerator in this talk and not GPU because specialization is your friend in this space because you can afford to specialize for small portions of your overall system, maintaining your flexibility in this space, managing your resources because your DPUs can help offload some of those resource management elements, and thinking about new ways to potentially build systems as long as you're not entirely focused on performance density. You can start thinking about performance per dollar, and this will be a larger footprint for you, but it may end up giving you more compute that's usable for more users in the end. And that's why we're interested in continuing on working on this, improving it more, working with networks and working with SmartNICs in the future as well to add all of that system software so that both traditional systems benefit from it and new potentials like composable infrastructure. So with that, I will end. Thank you very much, and I'd love to take some questions.
Are there questions, Brian?
Hi, Ryan. Very interesting talk. So I had it's probably a basic question here. So, in terms of the value add that the DPU is giving over the CPU in the disaggregated chassis, uh, is it basically a power benefit that the DPU is giving over the CPU? Or I'm assuming that every chassis will have a CPU already.
So chassis actually have no CPUs in them whatsoever. They're essentially just this big, gigantic PCIe switch at the top of them. We rely on the server back to the CPU. So having a DPU in it, we've essentially migrated a CPU into an environment where a CPU should not belong, right? In a traditional deployment like this.
Given like a mini CPU to the chassis already with the DPU.
Yeah. Which you needed the network there anyways, because you needed the high-speed network to be feeding your whatever's in that chassis, especially if you're doing things like AI. So you're essentially adding in something for free, but now the SmartNIC actually becomes the main controller in this space. There's still a major problem to solve in this space. I don't want to represent that you could just go out and deploy this today. We have, but there's still that issue of we need to be able to figure out how to reconfigure a PCIe bus such that the root complex can change in the middle of the computes that we can reroute traffic that way. Now, the programmable switches already let us do some of this, but there's the specific support for the DPU that still needs to be added so that we can do that without so that we can truly sever that connection if you wanted to back to that server. CPUs are still way faster. Like a traditional CPU server is still way faster than being able to feed a NIC with a DPU, for instance. So if you have a very short kernels and you're feeding a lot of kernels into your GPU, the DPU won't be able to keep up. You'll have to use a CPU with it. But for some things that use a relatively small, relatively much larger kernels, for example, like AI codes, it's easy. You're giving it so much work at any one given time that that control processor doesn't need to be nearly as fast to keep the GPU scheduler busy.
Thanks.
Any other questions?
Hi, Ryan. Thanks for the presentation. Just wondering how much is the power budget of a SmartNIC or a DPU?
That's a great question, Amit. So if I remember correctly, and don't quote me on this from the white papers, the non-GPU version of DPUs is well under 100 watts. I think it's like 60, 60, 70 from the white sheet. So I'll give you an idea, what can you get from a CPU side that has a TDP of 60 or 70 watts? Right?
Yeah.
Lots of stuff's creeping up into 300, 400 now when we start talking about CPU, just even CPU servers. Yeah, and more than that. And you're putting it next to GPUs that are consuming 2000 watts at the same time, right? So you want to drive that down in terms of being able to give that power budget over to the other components that are really driving a lot of your compute.
Okay. Yeah.
All right, let's thank our speaker.